Welcome to this explainer. Okay, let's dive into this. When we think about launching a vehicle off our planet, we usually focus on those massive rockets, right? The sheer thrust it takes just to break free of Earth's gravity. But honestly, getting there is only half the battle. Surviving once you actually arrive, well, that's an entirely different story. Today, we're exploring the intense, really intricate engineering required for spacecraft to survive, what is, without a doubt, the ultimate hostile environment. So I want you to think about that question for a second. Is space really completely empty? We've all seen the movies where spacecraft just glide silently through this dark, peaceful, seemingly pristine void. And it creates this persistent myth that once you're out of the atmosphere, you're essentially just flying through nothingness. But here's the reality. Space is far from a peaceful void. It is a relentlessly harsh obstacle course. From the absolute second a spacecraft clears the denser parts of our atmosphere, it's immediately bombarded. We're talking about a region packed with highly energetic particles, intense electromagnetic radiation, and microscopic matter that's constantly interacting with, and frankly, attacking the spacecraft. It's an environment that literally wants to destroy our technology. And this brilliantly illustrates our journey today. We'll start with the setup, move on to invisible threats, tackle fire, ice, and electricity, look at kinetic and chemical killers, and finish up by opening the engineer's playbook. Section 1. The setup. Approaching the void. So after pushing through that dense, lower atmosphere we breathe every day, a spacecraft enters conditions that are just fundamentally completely different from anything we experience down here on the ground. To really grasp where our spacecraft operate, we've got to look at the upper atmosphere, which basically splits into two major zones. First up, between 85 and 600 kilometers, we have the thermosphere. This is the neighborhood for most low Earth orbit, or LEO, satellites. It has extremely low density, sure, but it still holds on to residual atmospheric particles, and temperatures get super high because it absorbs solar radiation. But if you push even higher, above 600 kilometers, you cross into the exosphere. This is that outermost layer right before true deep space. Out here, gas molecules are incredibly sparse, and atmospheric drag is practically zero. And that's exactly what allows navigation and geostationary satellites to have those incredibly long orbital lifetimes. Section 2. Invisible threats, vacuum, and radiation. Now, just because the gas molecules start to fade away doesn't mean the danger does. Actually, it's really just getting started. We're going to look at this first set of major hazards that engineers have to outsmart, and the crazy thing is, they're threats you can't even see. The absolute defining characteristic of space is its near-perfect vacuum. There's virtually zero atmospheric pressure. Now think about this. Down here on Earth, if a machine gets too hot, what do? We use fans to blow air over it, right? Well, in a vacuum, there's no air. That means absolutely no convective heat transfer. If heat builds up, it literally has nowhere to go unless it can be radiated away. But it gets weirder. Without pressure, any trapped gases inside a spacecraft can rapidly expand. Liquid volatiles can instantly evaporate. And solid materials can even undergo something called outgassing, which means they literally bleed off gases. This can totally ruin sensitive optical instruments. Oh, and without air pressure, even just lubricating moving parts becomes this incredibly difficult puzzle. And while the vacuum is busy messing with your materials, the radiation is going straight for your electronics. Spacecraft are continuously getting blasted by three major heavy-hitting radiation sources. First up, solar radiation. Now, yeah, the sun gives us power via solar panels, but its UV and X-rays also degrade materials and cause some really intense heating. Second, we've got galactic cosmic rays. These originate from way outside our solar system. They're these extremely high-energy, highly penetrating particles that are incredibly tough to shield against, and they easily fry electronic circuits. Finally, there are the trapped radiation belts, better known as the Van Allen belts. Earth's own magnetic field actually traps these high-energy protons and electrons, and flying a spacecraft through these invisible bands requires some seriously heavily radiation-hardened electronics. Let's move to Section 3 and see how this builds. Fire, ice, and electricity. Thermal and plasma. It sounds like pure science fiction, I know, but this is an everyday reality up in orbit. Because there's no atmosphere to regulate or blanket heat in space, the temperature extremes are just shocking. On the sunlit side of a spacecraft, temperatures can absolutely skyrocket to a blistering plus 120 degrees Celsius. But then on the shadow side, it plunges to a bone-chilling minus 150 degrees. And here is the truly wild part. A satellite orbiting Earth can experience these massive temperature whiplashes within just a few minutes as it moves in and out of the Earth's shadow. This causes violent expansion and contraction of materials, optical misalignment, and some pretty severe degradation of battery performance.
And hey, as if wild temperature swings weren't quite enough to deal with, spacecraft are also flying through this sort of invisible soup of electricity. The upper atmosphere contains plasma, which basically means ionized gases made up of free electrons and positive ions. Now, when these interact with the spacecraft's surfaces, it causes surface charging. And if that charge builds up and arcs, you get electrostatic discharge. Basically, it's like a localized lightning strike right on the satellite. As you can imagine, this can cause massive communication interference and totally throw off vital sensor readings.
Moving right along to Section 4, Kinetic and Chemical Killers, Debris and Oxygen. Okay, so we've got a vacuum, radiation, extreme heat, extreme cold, and sparking plasma. What could possibly be next? Well, next we face physical impacts and chemical corrosion. This is the next lethal layer of our orbital obstacle course, 10 kilometers per second. That is the typical velocity of natural micrometeoroids zipping through space. These are tiny, often microscopic natural particles. But let me tell you, at speeds exceeding 10 kilometers per second, they pack an enormous amount of kinetic energy. An impact from something the size of a grain of sand at that speed, it can severely erode surfaces, completely wreck fragile solar panels, or even just punch right through thin structural walls. No problem. Now, what's really interesting about this slide is that orbital space debris isn't just large natural rocks or whole defunct satellites. I mean, consider something as simple as paint flakes. Up in low Earth orbit, debris is traveling at about 7 to 8 kilometers per second. At those speeds, even a tiny, stray flake of paint peeling off an old rocket can cause severe, literal mission-ending damage if it hits the wrong spot. And right alongside the kinetic threat of those high-speed paint flakes, we have a chemical killer lurking in the thermosphere, atomic oxygen. Now, down here on Earth, oxygen usually hangs out as molecular oxygen, two atoms bound together, O2. But high up in the atmosphere, intense solar UV radiation blasts those molecules apart. This creates an abundance of rogue, single atoms of highly reactive atomic oxygen. Over time, these atoms literally eat away at the spacecraft. They erode polymer materials, they degrade paints, they chew up thermoblankets, and they permanently reduce the efficiency of solar panels. It's like rust on super steroids. Finally, we reach Section 5, the Engineer's Playbook, Designing for Survival. When you stack all of this up, the vacuum, radiation, extreme temps, plasma, debris, atomic oxygen, honestly, it feels impossible to survive. But let's open up the toolkit of human ingenuity and see how we actually overcome this terrifying gauntlet. So the crucial point is that for every single hazard the space environment throws at us, engineers have developed a brilliant countermeasure. Because of the vacuum, we purposefully select materials that have high dimensional stability and simply won't outgas. Against radiation, we use hardened electronics and specialized shielding. To combat those wild thermal extremes of plus 120 and minus 150 Celsius, spacecraft get wrapped in multi-layer insulation, or MLI, and they're equipped with radiators and electric heaters to actively pump heat around. To stop electrostatic discharge from the plasma, engineers use grounding techniques and conductive coatings. To survive those high-speed micrometeoroids, we use layered, impact-resistant structures called Whipple shields. We even actively track space debris from the ground to perform collision avoidance maneuvers. And we cover critical components with specialized materials to fight off that highly reactive atomic oxygen. It really is an absolute masterclass in protective design. So, you might be wondering, why does diving into all these technical details actually matter to us? Well, it matters because a comprehensive understanding of this incredibly hostile environment is the absolute bedrock of modern space engineering. Fully recognizing these threats is what ensures engineers select the exact right materials and design ultra-efficient thermal systems right from day one. It protects those incredibly delicate onboard electronics from getting fried by cosmic rays, and it minimizes the catastrophic risk of kinetic damage from space debris. Ultimately, this meticulous preparation is what guarantees the long-term survival of the spacecraft. It directly improves the safety and the reliability of the missions we depend on every single day for global communication, navigation, and groundbreaking science. We've seen exactly what it takes to survive the obstacle course of Earth's upper atmosphere and near space. But as our ambitions push further, as modern missions aim for deeper space, way longer durations, and totally unprecedented complexity, the environment is only going to get tougher. Which leaves us with this final thought. With space missions growing longer and more complex, what new, unimaginable hazards will human ingenuity have to outsmart next? Thank you so much for joining me for this explainer, and keep looking up.